Let's begin with a word of prayer. Dear Father, we thank you again for this opportunity we have just to meet together and study topology, algebraic topology. We thank you for your many blessings, Lord. In your name I pray. Amen. Okay, so last time we talked a little bit about how algebraic topology can be used to prove theorems outside algebraic topology, I suppose. Today we're going to look at categories and functors, at least to start with. So here's the definition of a category from Rotman. Now, I guess I should confess I'm missing a word. The objects. The objects form a what? Set of objects?
For a small category.
No, this is for a class. Okay, so there's a class of objects. And let's see here, as he points out, we distinguish class from set. He says a set is a class that's small enough to have a cardinal number. So you can speak of the class of all topological spaces, but you can't talk about the set of all topological spaces. And then he has a little litany of everything that's allowed in our set theory. And basically the point is to introduce the term class instead of set is to avoid the stupid Barber paradox, more or less. I mean, it avoids that trouble that Cantor's set theory gets into with the self-referential. I don't know. This, what he says is...
Russell's paradox.
Yeah, Russell's, that's the one. Except, everything's permissible, except the statement X an element of A is always false whenever X is a class, and that is not a set. So that gets the almost by definition gets the class out of the trouble of the paradox. Anyway, morphisms are maps. I suppose, what are they? Well, they're morphisms. For any pair in a pair of objects, you can find a morphism from one to the other. And then you have this notion of composition, right? And the objects, the morphisms, the composition have to satisfy certain axioms. The family of morphisms from A to B are pairwise disjoint. What's that mean, Nathan?
Oh, well, they're just treating it as a set. So in order to uniquely identify each morphism with a homomorphism from one object to another object, in their formulation of a category, they just want the sets to be disjoint. So given a morphism, you can identify its source and its target. In fact, that's another way of axiomatizing it. Instead of saying disjoint sets, you just associate each morphism a source and a target object. But this is just the way that they chose to do it.
Oh, okay.
So there are different approaches. Actually, quite a few different approaches. But
I see. So you're saying he has a version of category theory which suits our purposes here, with a minimum of categorical discussion, let's say.
Yeah.
Yeah. Okay.
Actually, if you want to be really minimal, the only objects are the morphisms and the composition map. Composition map being a partial map instead of a total map.
Interesting. I definitely don't know that. Let's see, your composition is associative where defined. I mean, that kind of is what it is. We saw this last time, right? That the identity map maps to the identity map under the, well, I guess we haven't. The thing we saw last time was the functor. We're not there yet, right? This is just that there is at least the identity map in the morphisms. Minimally, there's that. And yeah. So what you were just saying basically is that this. So he says, if something's a morphism, what do? You can write it. What is it? So it's like if F is a morphism. From A to B. In other words, if it's in this, right? Then we denote what? We say F is a mapping from, like that. But I guess that doesn't actually have to be a function.
Nope.
So, but I do, he points out that a morphism is, what does it take to uniquely define a morphism? He says it's uniquely defined by the domain, the target space, right? And then the graph. A is the domain, right? I guess this is a subset of the Cartesian product, what, A and B?
Wait, what page does he make that claim on?
7?
7?
Yeah. He says, let me read carefully. This may be an example rather than a general comment. Our requirement in the definition of category that Hom sets our pairwise disjoint is a reflection of our instance, like you were saying, that a function f from A to B be given by its domain, its target, and its graph. Right?
Yeah, so it's not morphisms, it's functions.
Yeah. Okay, so this comment I'm making is about functions, I suppose. So anyway, I mean, I really like what he says, that, basically to distinguish between, if you have A, a subset of B, right? You have the inclusion map, which is a mapping, from A to B, right? And then you've got the identity map on A, which is a mapping from A to A. They have the same domain.
Same graph. Oh,
Right. I think they have the same graph even. But they have different targets, so they're different. And then you have other one. He has another example where you have the same domain, same target, but different graphs, so they're different, But so then I won't do too much writing here. So basically, if you look at the class top, right? So let me just actually let me get rid of this and list these here. Should do some writing. If I can find my eraser. Ah, there it is. So let's see here. He's got this marker's not very good. Find one that's actually readable. So here. Hello.
How are you?
Pretty good. How are you?
That's where you hang out now, huh?
Yeah. Usually. What you up to?
I'm just looking around, trying to find Dismore. I don't know where he is.
He should be up on the 4th floor.
Yeah, I was up there, but
I was thinking maybe down in the lab.
thought he might be in lab, but nobody's there.
Oh, maybe he went golfing.
I'll find him
Okay.
if he's here.
Good to see you.
You too, Jim.
I don't know, Professor.
That's Dr. I know his name. This is, Van Eaton. James Van Eaton. He's one responsible for the observatory getting put up, among other things. He started being a professor here when I was born.
Wow.
I think he's still teaching the astronomy classes these days. Let's see here, or he will from time to time. Anyway, so topological space. So the category of top the class, the objects are topological spaces. What is something like this? These contain what? These are what? These are continuous functions. Right?
Wait, what is top? Oh, topology. Sorry.
This, the topology, that's the category. Category topological spaces. Continuous functions are the morphisms, right? At this point, he introduces a definition to talk about a subcategory. So, basically, if you have, try to run through it briefly here. If you have a category and another category, I guess I'll do it like this. With what do you need? You need the objects of, so C is going to be the subcategory of A. So like the objects of C are inside the objects of A, right? And so if A and B are objects of the category C, you can do what? You can either talk about, you have two different options at this point. You can talk about the morphisms relative to the first category, right? Or you can talk about the morphisms relative to the larger category, right? In this context. He says C is a subcategory of A if which is a subset of which. You need that, if you'll allow me a vertical inclusion, like that. All right, so the Hom C has to be a subset of Hom A as appropriate for all possible A and B as in C. And the composition has to be the same in C as it is in A. In other words, the composition is a restriction from the larger category. I won't write that all out. So the topological category, the top category, has many interesting subcategories, right? Like what are nice subcategories?
Hausdorff spaces.
Yeah, Hausdorff spaces. What else we got? Now, of course, to be careful, I should really do this, right? The topological category. So what are choices for the C? Like you said, Hausdorff spaces. I think you list Euclidean spaces as another category. What else do you have here? Oh man, I lost my page. There's a truckload of them. Compact spaces, so on. All right. And you can restrict the maps to be differentiable or analytic, and so forth. So even inside these, inside Hausdorff or Euclidean or compact, if it makes sense, you can also restrict the morphisms down so that they're just containing either like analytic functions or whatever particular. If you can find some notion of morphism, some notion of function which is sort of closed under composition, then you can potentially make it a set of morphisms for this subcategory, right? Another example, of course, is the category of group. So groups, and again, groups have a bunch of interesting subcategories like what? But before I get to that, I'm just going to forget the subcategories. It's category group. What are the homomorphisms here? Oh, I'm sorry. I think I just spilled the beans. So these are, like we said, homomorphisms, okay. You can also look at the category rings, right? And then homomorphisms would be ring homomorphisms, right? Now this one's interesting. You can look at a category called top squared, right? What's so the category, this is basically, it's a category of pairs of topological spaces. The objects are pairs of topological spaces.
Don't
Yeah.
they use, I thought it was a topological space with a subspace.
Yeah, you're right. Yeah, I should be more specific.
Which actually is odd because the square of a category is actually a standard construction, and it actually should be pairs of topological spaces, but they use something slightly different.
I think then
So, like,
this is another example of Rotman's pedagogy. Right.
how so?
He's made the definition non-minimalistic as to avoid discussion, which is not interesting to him. This is another instance of that.
Gotcha.
Yeah,
Yeah, because I was wondering about that
he's a
when I was reading
mathematical
it.
politician. I mean, in a good way. Okay, so my belief in words having meaning that I expect them to mean was correct according to your larger study of category theory. But I mean, this is what he says.
Yeah.
But yeah, it's supposed to be here. A is so in Rotman anyway, he means this to be a subspace of the topological space X. I would assume, given the subspace topology, if I had to guess. And a morphism, right? So B has to be a subspace of Y, and the morphism is actually a ordered pair. It seems like you shouldn't use F for the ordered. This seems wrong to me to say that this is F is equal to F prime. That is that. I don't know, that seems sketchy to me. But he says where F from X to Y is continuous, and but fine. I mean, I guess that's maybe there's no danger of confusion. Whatever. So here, if it makes you feel better, we can put a vector over this one. Yay! So now they're different. Anyway, the point is F is the continuous map from X to Y, because we're in the topological category, right? And F prime is
restricted to it.
yeah. I don't know if he says that. Well, yeah, maybe he does say that.
Well,
He says that in maps. He says where F, yeah, Nathan?
oh, I was just going to say, yeah, I think that's required by this commuting diagram he has here.
He says Fi equals I F prime, or is it J F prime? J. Yeah, let's see what's the diagram. Here we've got A, here we got X, here we got B, here we got Y. So this is the inclusion. Here's the inclusion downstairs. This is F prime, I assume, and this is F. Yeah, so F composed with I is this, right? And J composed with F prime is that. So those compositions are equal. But like you're saying, that's tantamount to the diagram commuting, right?
Right, so F of I is just F restricted to A.
Yeah. Right. We can
And then J of F is just the extended function.
yeah. Right.
Function with extended codomain.
Cool. That's nice though. There's like a nice mapping level, how you do restriction and extension. the level of maps, this is how you do it. Now, the reason I really like this example is what he says next. His next category is top star. So this is the category of pointed spaces. It's a topological space paired with a point. So a point is kind of a stupid subspace. But these are important. This is important to the study of homotopy and other things where we actually work in some kind of pointed category, not technically the category of topological spaces, but we also carry a point around. So this one's pretty relevant. Let's see here. I don't know if I really have much to add to this chapter. You really should read it. Definition: a diagram in a category is a directed graph whose vertices are labeled by objects of the category and whose directed edges are labeled by morphisms in the category. A commutative diagram is a diagram in which for each pair of vertices, every two paths composites between them are equal as morphisms. So that's, again, an example of a commutative diagram. Then talks about a congruence. A congruence on a category is an equivalence relation on the class of all morphisms. So it's, I guess I'm going to have to erase all this. That's okay though. So you guys are by now experts in category theories. You know these things? That's true for at least one of us. Let's see here. I'm not included. Let's see here. We haven't gotten to the part of this section which resonates most to me. So when we get there, Nathan may already know. Definition: a congruence on a category is an equivalence relation on the class. So it's the union over pairs, right, of homomorphism, of the, morphisms, I should say, maybe, such that let's see here. What does it take to be a congruence in the category? If F is a homomorphism, a morphism, sorry, I'll get to it eventually, and F is equivalent to F prime, then that implies what? Fill in the blanks here for me.
First one is F prime is equivalent to F. Or is that kind of silly?
It's just that F prime is an
It's
element.
also or homomorphism.
Yeah. And the next one implies that G composed with F is equal to G prime composed with F prime. I don't have much intuition for what's going on here yet.
Like equal or equivalent.
Equivalent, thank you. Wow, I'm very popular at the moment. I keep getting emails. I wonder if somebody proved the Riemann zeta hypothesis or something and it's coming in my inbox. Usually, sometimes, you never know. Then he has a theorem. If you have a category with a congruence, and if you let bracket F denote the equivalence class of the morphism F, then you can define a new category, category prime as follows. The objects of category prime are equal to the objects of the category, And the morphisms of the primed category are the equivalence classes of the morphisms of the original category. And you also get that the composite of the equivalence class is the equivalence class. Yeah.
Yeah, it's the equivalence class of the composites.
Yeah, sorry. So you get this. I should be able to say this in words, but there you get that. So basically the C prime category has the objects of the C prime category are the objects of the C category. The morphisms rather of C prime are just their equivalence classes of morphisms, right? Of the original category. And you get this. Actually, I mean, he's defining composition here, okay? This is a definition. So if you define composition like that, and you build this new, given an equivalence, given a congruence on a category, you can define a new category, C prime, according to these rules, and that gives you what's called a what?
Quotient category.
Yes, indeed, a quotient category. As he says, the most important quotient category for us is the homotopy category described in chapter 1. Excuse me. All right, so next we talk about functors. What does a functor do? So here's the definition. If you have a category A and a category C, right, then a functor, which just sounds awesome, doesn't it? So here, from A to C is a function that is one if A is a object of category A, then that implies that TA is an element of the objects in category C. Right? 2, if F from A to A prime, dimorphism in A, then TF is going from TA to TA prime is a morphism in C. And also we have that T of the composite is equal to the composite of the functors. That's 3. And then 4, we have that the functor of 1 is equal to the one of the, like we did last time, in the particular context of the homotopy. Like he said, our earlier discussion of homology functors Hn cannot be rephrased. For each n greater than 0, we shall construct a functor h sub n from top to ab. He's like, so in terms of the notation just introduced, hn is a function. I mean, it's a functor, but it's also a function from the class of, from the category of topological spaces to the category of abelian groups. So that's what we did last time. All right. So now he throws out a few interesting functors, like I think the one I most identify with next comes up, the forgetful functor. This one basically it takes, for example, you can take from the category of top to the category of sets, and it just takes basically the topological space and strips off the topological structure and just leaves them as sets, and morphisms become just function. Homeomorphisms become bijections, and continuous functions just become functions, and so forth, under the forgetful functor. You can also take groups to sets, or abelian groups to groups, or abelian to sets, and so on. There's an identity functor on any category. If you have a fixed topological fixed topological space, he says Tm from top to top is a functor, where Tm x is x cross m. Let's see here, what is that? What is that?
It's the topological product.
Ah. Oh, okay. See, what's his next example here?
How does the functor acting on a function affect in that case?
Yeah, right now. Let me write it down here.
Also, is there a different term? Do you say the functor acting on an object versus the functor acting on a morphism, or is there a special?
Let's see.
Calling it.
Oh man, I just erased it. He said a functor is a function, right? It goes from category A to category. I guess the thing is, the category is what does it take to make a category? It's not just. A category is made of three things in Rotman's world of category theory: objects, morphisms, and also composition. All three of those things have to be mapped by a function on a category. So it makes sense to either take you can either take a functor of the of the set, of the morphism, or of the composition law. All three of those things are defined for a functor, because the functor is a function from the category.
Got it. Okay.
Yeah.
I was just wondering if there are different names for it. The different actions.
That would be a question for Nate.
I don't think it's in here. I know on the map on objects is typically called the object map, and I think the map on morphisms is just called the morphism map. There's something like that.
Yeah, that certainly makes sense.
M, a topological space, a fixed topological face. I keep saying topological face. What's wrong with me? He says Tm from top to top. A functor is functor, where he's defining it as follows: Tm of x. This may kind of answer that. This may also address that question, actually. So it's x cross m, and if f from x to y continuous, then Tm f is mapping from x cross m to y cross m, defined by xm maps to f of x m.
Seems kind of boring.
It does seem kind of boring, doesn't it? It seems to me what this is doing is, well, yeah, I don't know, I mean, like, why?
I think, from what I read, it's
Yeah.
probably relevant to like homotopies relative to a subspace. Or like a homotopy that keeps a subspace fixed.
Okay. So these mysteries will all become clear to us in the next chapter.
Well, not the next chapter, but
Okay, but eventually.
further in the future.
But then the forgetful functor will come into play for me. Let's see here. He also then defines a contravariant functor. And then also a covariant functor. Right? And then he also talks about dual space functors in the next example. So we will again talk about that structure as it arises later. I'll leave it for when it comes up. And finally, an equivalence in a category is a morphism from an equivalence in a category C is a morphism F from A to B for which there exists a morphism from B to A, such that the composites are the identities on B and A respective, as would make sense. So, and then his
That's interesting.
theorem: A and C are categories. T from A to C is a functor of either variance. Then F an equivalence in A implies that TF is an equivalence in C. That's actually really, really important. You see that playing out in really interesting applications of category theory, where you have this ability to transport like homeomorphisms to diffeomorphisms, or isomorphisms to homeomorphisms, and so forth and so on. These if you have an equivalent, a bijective invertible with both notions, structure preserving in both directions in whatever category you're working in, and you have a functor, you can move that kind of bijection to the other category. I think that's where category theory really shines. Anyways, what I think is interesting. But you're about to say something, Nathan.
Oh, I was just going to say easily that's just called an isomorphism.
Not an equivalence.
Now, equivalence actually, where I've seen that used, is actually a specific notion, well, I guess at least specifically between categories. Because there's actually a difference between two categories being isomorphic and two categories being equivalent.
So I think what I've gained from this is this discussion. It's good to read the section. It's good to try to understand it. I wouldn't dig too far into it, because if you want to study category theory more in depth, you should look at something that's that's just category theory. Like, for example, this. Not that I've read that, but I've heard I should read it. Anyway. Oh well, maybe once I finally have a student who's interested in category theory, I'll work on it. Once my teaching load gets reduced, to 2 or something. Well, we are a Research 3 school now, so it's only a matter of time before the teaching loads get lower. Research 3.
What does that mean?
What does that mean? I don't know. We're it. Let's see here. We have arrived. Okay. How much time do I have left? Let's see here. When do we end?
I think you said 25.
Was did we say 3:30 or did we say?
I think you had said you might have a little bit more time to get ready for count 2.
Oh, okay. So we should go till 3:25 unless I'm very inspired. Or something like that. Okay, so But that's mostly the purpose of category theory for us. It's not so much something to use to prove things. It's just a point of language at this point, right? Now, hopefully, Nathan, when you'll talk about natural transformations, you might do something a little more substantial when you host this discussion. Yeah. So that brings us to homotopy, right?
I should figure out how to talk about actual equivalences.
Actual what?
Equivalences between categories.
I wonder how much of a fight that chapter will be to you, given that you have other pre-existing notions of categories that it might not.
Just their notation, I think, mainly.
Okay, that's good. That seems appropriate. I mean, category theorists should be flexible. Let's see here. If X and Y are spaces, I would assume topological spaces. And if F naught and F1 are continuous maps, from X to Y, all right? Then F naught is homotopic to F1 if there exists a continuous map F, big F, from X across the unit interval I to Y. Now that I again is the real 0 to 1, right? Subset of real numbers, that guy. And what are the rules of the game here? You have to have, when you plug in time 0, I think of this as being time. Just intuitively. So if you plug in time 0, F reduces to the 0 map. If you plug in time 1, F reduces to the 1 map. Right? And that's true for all X and X, of course. Alright, such a map F is called a homotopy, and if it is the case that such an F exists, we usually write F homotopic to F1 like that. Okay.
What's also interesting that I've seen notationally in this book,
Mm-hmm.
they will often write capital F colon F naught equals squiggle F1, which is interesting because that's used a lot in type theory, where you'll have something on the right side, it's like a proposition,
Mm-hmm.
and on the left side is a proof of that proposition.
So you're saying write F?
Yeah, they will say F colon F naught homotopic F1
Oh, like that.
to mean that
This F.
F is
all
a
of
proof.
this.
It's a proof that F naught and F1 are homotopic. Is
Oh.
one way of thinking of it.
F is a proof. Yeah,
Yeah.
that is in fact what's required to prove that they're homotopic. Yeah, the existence of set F. Yeah.
So it's a nice notation.
Oh, okay.
Or another word you hear is
I feel like
maybe
I've
not in this book, but it is witness. F is a witness to F naught and F1 being homotopic.
Ah.
Actually,
that is kind of snazzy terminology. I think I've seen this before somewhere, but the primacy of F is nice there. It's like it's okay.
Yeah, it's interesting. I don't know, like, if the chicken came before the egg or whatnot, but essentially, in type theory, you have the notion P dot X equals Y, which means P is a proof that X is equal to Y.
Ah. I don't know.
So, like, I don't know if that notion came from this or if this notion was influenced by that, but
I don't know, I guess.
interesting history question.
Yeah. I suppose. Let's see, if I actually had like graphs, like this was the graph y equals f1 of x, and this was y equals f2, f naught of x, something like that, right? Then you can kind of imagine if you had f somewhere in between, that'd be something like y equals f of x comma t for some t between 0 and 1, right? And so it's kind of like, it can be deformed, they could be moved one to the other or something like that. But of course this picture is harder to draw when your functions aren't real valued functions and a real variable. And I'm not sure how useful this picture actually is, but I'm going to get rid of it before someone documents it. Alright, let's see here. No too much. Okay, so here's the lemma. 1.1. It is a gluing lemma. It simply states the following. If you have X as a finite union of closed subsets, X equal to union I equals 1 to n of xi, where x sub I closed subset of something, closed subset of what? You didn't tell me that yet.
I guess this topological space,
Yeah.
whatever they're working under.
Oh, I guess subset of X. It's kind of
Yeah, kind of
yeah.
tautological.
Yeah, but okay. But anyway, they're closed inside X, and then also, and if you've got continuous maps, Fi. This kind of makes me worried. I remember when I took. Oh, you know what it was? When I took manifold theory, we did a gluing lemma, and something bad happened in the lecture, and it ate like 2 or 3 days of my professor's time. So hopefully that won't happen to us. Let's see here. I forget what happened, but there's more structure to keep track of in a manifold theory course, right? All right. Anyway, so these are continuous. For each I. And they agree on overlaps. It's, in other words, if you take Fi restricted to xj, it's equal to fj restricted to, well, let's say xi intersect xj, right? I think that's consistency on overlap. Wherever there's an intersection, the restrictions agree. Then there exists a unique continuous f which restricts to these f sub i's on the whole of X. So this takes us back to calculus 1, right? We have those functions. Prove this functions, choose an A, which makes this continuous on the whole real line. Kind of nostalgic, isn't it? Let's see here. Of course, we face a slightly more abstract problem, but the basic idea is the same. Let's see here, here's the proof. He says, it's obvious that f is defined by, well, first of all, yeah, proof. Point number 1, you clown, you know how to identify, you know how to define f, right? F of x is equal to f sub I of x if x is an element of x sub I. Alright. So that defines a function.
A unique function.
That defines the unique functions. It's single valued. Well, I guess maybe that's a question. I don't know, but no, I think it's
No, it is, yeah.
single valuedness is given by that,
Right.
Yeah.
right? So he says the unique well-defined function, and it's also obvious that f restricted xi is equal to fi for so constructed a function, right? So continuity is what we worry about, right? He says if C is a closed set in Y, all right? So C is a closed set in Y. Then, if you look at F inverse of C, right? That's equal to what? That's equal to X intersect with F inverse of C. Well, that's kind of tautological, isn't it? I mean, X is the universe where F maps back to, so it seems hard to escape that. And then he uses that this, of course, is the union, finite union, which is assumed in the theorem, right? Precondition here. All right, what's his next move?
Do you distribute?
Yeah, let's see here. I think this is just a set theory.
Yeah.
Intersection.
So the union of the intersection of a finite union is the union of
The intersection.
the intersections, yeah. All right. And then he says that that is equal to his next thing is to say that that's actually xi intersect with fi inverse of C. Does that make sense? Why?
Because when we're looking at the intersection of xi with f inverse of c, we're only on xi. And so, kind of when we're looking, when it only maps to x, or when the inverse image is only on xi, we can just consider fi. And it wasn't well explained.
Right. I think I believe you.
I mean, I'm sure we could do like the double continuum.
So the yeah, but I mean, I think that's I mean that it's because the inverse image
Intersect xi.
xi can only contain points in xi, and f agrees with f sub I on all such points.
Yeah.
So we can replace this with fi. Yeah. But then this is just. But agree, if I was to supply extra detail, I would try to prove the double containment of that. That I think is the one step that's not just been basic set theory. And Dr. Dinsmore's popular today. Let's see here. Some I equals 1 to n of f spy. But, what do we assume?
Continuous.
That's closed. This is continuous. Inverse image of closed is closed. And so you've got a finite union of closed sets, which was once more closed. So we just showed that the inverse image of a closed set is closed, and that suffices to prove continuity of F. Right? Hey, we actually did a real proof in here. Yay. Sort of. Okay. He says there's another version of the gluing lemma used on open sets whose proof is that of lemma 1.1 mutatis mutandis.
Yeah, I feel like it'd be pretty much the same thing.
I believe that is the meaning of what I just said, yes. Pretty much the same thing. Yeah, right. Okay, so then here's theorem, and this is the theorem I hope it's proved today. Homotopy is an equivalence relation on the set of all continuous maps. Alright,
Should be too hard.
from X to Y. Let's try to prove that. I think we don't need the, yeah, I think we don't need any of this really. You guys might remember homotopy from our brief stint in advanced calculus.
Yeah.
We should just refer to those videos and not do this.
Just refer to those videos. Yeah. The unfortunate thing is, while you guys remember a fair amount of that, I probably remember none of it. Theorem. Homotopy is equivalence relation on set of all continuous maps. So here's the proof. So first of all, let's look at reflexivity. Suppose f is going from x to y, and we want to show that f is f is reflexive. Is homotopic to itself, right? Okay. So how should we do that?
Make big F of x t and just be f of x for all t.
You said like f of x
Yeah, t.
comma t just equal to f of x. So then you have f of x comma 0 equals f of x comma 1 equals f of x. Yeah.
It's more boring than the.
Definitely continuous.
Yeah, it's more boring than that functor we had.
It's even more boring than the, yeah, it is more boring than the functor that we couldn't understand. Well, we don't yet appreciate, I should say. So, yes, therefore, f is homotopic to itself. How about symmetry? So suppose you have f and g, both functions from x to y, and suppose f is homotopic to g, right? That means that there exists an f from what? From x cross I to y, such that what? F of x0 equals f of x, and f of x1 equals g of x for all x and x. So construct g from x cross I to y by what rule?
G of xt is f of x1 minus t.
Say 1 minus t?
I think so.
Right. That's clearly continuous because it's the composite of a continuous function with other continuous functions. And you can easily see that 1 gives you 0 and 0 gives you 1, which turns the tables on f and g and shows that g is homotopic to f. So this in type theoretic lingo so much less writing. Thank you, Dean. But if I said it correctly,
Have you said it correctly? What did you say?
this.
Looks like you wrote it.
You wrote it correctly. Yeah. What did you say?
I don't know what I said. That's gone forever. I said that like a whole 30 seconds ago.